Um, hang on. I thought I'd written down. Can you tell me the name of the government funding agency that you're working with?
Well, the lab is Oak Ridge National Labs. It's part of DOE, Department of Energy.
And what's the acronym?
It's New Frontiers, ORNL is Oak Ridge National Labs, or DOE.
Yeah, but there's another one. Something NAT.
Something NIT.
NAT.
I don't know that one.
Well, it's Netcast.
Netcast. Okay.
It's called the Netcast NFCC Consortium. I thought they were your funding, your proposed funding partner.
No, well, the one we're trying to go for is the RFP, the New Frontiers.
Okay.
RFP, which is coming out of Oak Ridge National Labs, and I believe it's part of the DOE funding.
Oh, okay. So maybe that's why I have not seen it. It's the stuff I've been working with is commercial, not DOE.
So maybe we should be going for NAPMP funding with Subu?
Well,
I mean, that might be a better one.
To be honest, let's see. I hate to say you shouldn't do it, but I'm not sure it's a great fit.
Oh, right. Okay. Yeah, it's advanced packaging, so it's within the chip, isn't it? It's the chiplet side of it, really. Is that right?
Including substrates.
I mean, when Subu was a professor at UCLA, I presented what we're up to him, yeah. And he said he could try, within UCLA, he could try and apply for some research funding. He was sort of thinking it might be worth doing that, but that was under UCLA trying to get funds, as opposed to giving funds.
Yeah.
Okay, so I mean, Mbappe's obviously Mbappe knows what we're up to.
Yeah, he'd be a good guy to ask because he was very active yesterday.
Yeah. I mean, obviously now with their government hats on, they can't say anything really. I mean, it's a case of all they can do is encourage you to apply, right?
So I gotta tell you something that probably revealing about me, but in the afternoon they were trying to encourage teams to where people in the audience, and there was a big audience, would state what was their interest.
Right.
And hopefully someone else would say, oh, I have something that can work together with that, right? And so they wanted to create this kind of social engagement between the different teams. Okay. And it was pretty chaotic and might have been very effective, but I don't work well in that environment. I'd rather be behind the scenes, contacting somebody with a very thoughtful message and, trying to go about it that way.
Right.
And so that's what I'm doing. I realized that in the NAPMP work, there's a first phase, which is a concept paper, and that's due in just a matter of weeks. And then the second phase is the full proposal. Okay. Now, the full proposal requires a bunch of things. It requires that you're registered with sam.gov. It requires that you're registered with grants.gov, and it requires things like that you have in place a policy for securing your IP.
Oh, right.
And all of the,
Yeah, because they want to keep it within the US, don't they?
yeah, and you know, it's all important, but they're not things that I want to expend
No.
my energy on,
Tell me about it.
right?
You and me are cut from the same cloth there.
Right. So I am actively looking for a partner who wants to lead the proposal, and it already has all of these things, you know.
Yeah.
So are you registered with sam.gov?
I do get some messages, but I don't think I'm officially registered. I think I only got acquainted with it with the solar stuff because I was using their solar prediction software or whatever it was.
So it turns out you can't get any government money without being registered with sam.gov. And you can't actually get any money
Well,
without also.
so I think that this is where, I mean, just go. I think there's similar issues with this DOE funding, this Oak Ridge National Labs that we're trying to go for, right?
Yes.
And this is where we need this system integrator. And ideally, you want a bit, you know, the one at the top of the tree of the people working together needs to have these sort of certifications, as you're calling them.
That's right. That's right.
And so Bob Ciotti, that was the CTO of NASA, and he really liked what we were up to. He's retired, and now he's working for one of these value-added resellers that work closely with the government. So they're like they resell IT equipment into the labs, and they have engineers that support the IT equipment in the labs. So they're like on site.
Yes.
So I get the impression they've got all of those qualifications of how to apply, what forms to fill in, how to tick the boxes, and all the rest of it. So I was encouraging Bob. I seen him a couple of weeks ago, and he was going to take a look at at what we've done so far, and he was on about maybe putting some words in to help us from his perspective, as you know, from his NASA perspective, with NASA sort of hat on of what they like about what we're doing.
So that's a very valuable.
It would be, yeah, but
yes.
so I you know, he's just new in the game. I know he's pretty damn busy there, so I probably need to give him a nudge.
Okay, so I'm trying to give you a warning that without that connection, you won't get any money.
Yeah, no, that's fair. And they made that explicit on that call, did it?
Yes.
Okay, if you know where the recording is, could you send me a link to it and I'll watch it.
I don't think it's available yet, but if it comes, I'll try to do that.
All right. Yeah, no, that's fair enough.
Of course, it was multiple hours, you know.
Yeah, right.
Yeah.
Yeah, shame I missed it. Okay.
Yeah.
All right. Okay, on the thermal stuff.
Yeah.
Were you at last week's meeting, the main meeting, as well as the thermal one a couple of weeks ago?
Not the main meeting, just the
Yeah,
thermal.
so I basically did a bit of a rundown of all the work groups that we've got activity going on in, and Trent DeHooge from Lawrence Livermore Labs, I think. Hello. He highlighted the challenges with the Frontier machine and other machines with using water and the growth of water with bacteria and all the rest of it.
Okay.
And said it was an absolute nightmare. And all of the extra copper area they put in to get more water touching the copper for the heat transfer.
Yeah.
Ends up being a very good filter. And these growth things that grow where there's turbulence in the water flow and there's stagnant water, that's where these particular bacteria love the warm water, and they grow, right?
Yeah.
And they don't detect it in their sensors, etc., until it's too late. So something breaks off from the growth and then starts to block the filters.
Yes.
And so it causes an absolute nightmare. So they mix the water with something called PGW, I think is one of them, 25% that, but it's a pretty nasty substance. And it doesn't make it quite as firmly conductive. So anyway, long story short, he actually arranged a call with somebody that had more direct experience with it. But it was a really good discussion that we had a couple of days ago.
Is
And
it possible you could send me a link to that discussion?
unfortunately, that wasn't recorded. It was just an offhand call I had with them, so I don't
Okay.
have it. But
I'm very interested in this topic, and if it comes up again, I'd like to know about it.
yeah, well, so I was thinking that this, in talking to these guys are the labs, and their experience is basically they're going, water is a nightmare. We're going back to glycol, or
Okay.
we're going to load the water with this PGW or whatever. And sod the sustainability, sod the environment. Well, they're not basically saying that, but that's the sort of water's too hard.
Yes.
And what I took away from it is we've stumbled into using water. And I mean, it has got used, like in various situations, but is still only just being adopted, right?
Yeah.
And I guess in the old days, Cray and IBM used more of these dielectrics, right? So therefore, anyway, so we've got this desire to give up. It's just too hard, right?
Uh-huh.
But what I realized is I said, has anybody actually sat down from an expert perspective and said, well, okay, we know these things that happen. How do we stop those little stagnant pools of water? And I said, with us, we're trying to make the water hot. So 65 degrees C would kill all of these bacteria that love to live in these warm temperatures of 40 or less,
Yes.
which is what they're operating at. And they're saying they're looking more at the cold end, because if they take it to the cold end, then these bacteria don't survive. And nobody wants their chips to run hot. And I do worry about running the chips hot for sure, because your leakage goes up, right? But leakage is I think leakage is an exponential function of,
Yes.
so you get thermal runaway when you get too hot, right? But that's around about 100. When you get above 105, 110, that's when you get the thermal runaway. Whereas I think once you get down to something like in the 60 area, certainly, or below 85, you're back in the straight line of the other side of the exponential curve.
Yes.
And then it's a case of, we've obviously got more leakage as we run the temperature hotter. But what percentage of that leakage versus the power needed for the frequency of the chip running? Is it 10% leakage or 50% leakage at 85C, let's say?
Yeah.
And so the question then begs is, if we're boiling at 65, then maybe we can kill a lot of these things. But by the way, I've started asking ChatGPT. It gives you very, very good answers in terms of guiding. Because I said, hey, what temperatures do bacteria grow? And it says, well, there are bacteria that will grow at 80 degrees C. You find them I guess, in the sea around the lava, around the lava zones around the weak areas of the crust, I guess.
Yeah.
But then I was thinking, well, actually, what if you did oscillate the temperature? You know, what if you sort of run the computer at different temperatures as well? So you could maybe say, well, we're going to run this one cold for a couple of, or we're going to run this one very hot. We're just going to take it up to make sure that the entire loop is 85C or 65C. The dyes are, the water's at. And so you make sure that everywhere it gets, and it's going to kill any bacteria before it even establishes any significant growth. But then they were sort of saying, well, nobody likes their computers to be idle. So they don't want to say, I'm going through a water cleaning cycle, so the computer's not running.
Right.
So anyway, so there's a thought process, but I'm thinking that, and they're saying if you use, apparently deionized water is not a good idea because it really does make material wear. It's not very conductive. So you don't want to deionize water, but if you purify water, and I've been in that game, by the way, with my swimming pool, you know, if you take out all of the, like one thing I do is I've got a phosphate remover. Now, obviously that's not, you know, in a pool, it's a different situation, but all I'm saying is the algae just doesn't grow if the phosphates aren't there in my pool. So if you make sure you put in good clean water that's had any of the horrible materials removed, then, you know, as long as you do that, then it's a closed loop, then it should stay in a pretty good situation. Then if you add the boiling stuff that, you know, or where we're raising the temperature above 65C. So all I'm saying, all I was saying to them is, if we actually design this bloody thing with this thinking in mind of all of the troubles of water, but we successfully use water, then it's going to be a tremendous win.
Yes.
And from a sustainability and an environmental perspective, it's a huge win. So a government ought to be delighted to fund somebody that says, don't give up on water, let's design from the ground up for water.
So my question is, why not use an antibacterial agent?
Well, so that's what they do, right? But I think this PGW or whatever. So they say you can treat the water and all of that, but then that starts to bring these horrible substances in. And it's, I think it's PGW. I did take some notes. I could send you the notes. And they said it's 25% PGW, 75% water is their mix.
Well,
but the other thing, you know, I said to them, I said, well, if this conformal coating works like a NANAD at University of Illinois if that works, NANAD is claiming that's 7 times more lower thermal resistance to heat transfer from the silicon to the copper through the conformal coating insulation in a standard grease and copper being pressed. And if that is really 7 times more efficient, and then your claim of if we boil is 7 times more efficient, that's 49 times more efficient. And then if we say we use water instead of the best dielectric, water is twice as conductive as the best dielectric. That's 100 times more efficient.
Yes. So I think.
Then the other guy said, well, yeah, you wouldn't need is close is bigger copper surface area then to transfer the heat from the copper to the water, so your filter wouldn't necessarily get blocked up if it did get, and you could have a filter somewhere else.
I see. I think NANAD though is promoting the use of surface treatment. I saw in his paper a photograph of the surface, and it looked like oh, I don't know, a scaly growth on the surface.
Oh yes, yeah, making it sort of rough.
Yes.
Yes, yes,
And
yes. Yeah, that gives you a little bit better surface area, right, right, for the
but
transfer of the
but
heat.
I have to imagine that any bacteria would just love to be hiding inside that.
True.
Yeah.
But again, if it's flowing, so where this happens is that what they said is they when it and it happened with, I guess it happened with IBM as well. When a machine went down, they put in these hydrochloric acids or whatever, so something to flush the system through and get rid of this bacteria. And they still couldn't do it. And so they actually decided to dissect these things and take it apart, and they'd find this bacterial growth in bizarre corners. And then when they looked at it, I mean, it's like they said, if you had a bit of a turbulent flow somewhere, you'd also have a dead patch. And that was where this stuff would grow, because it liked to grow in small, calm waters. And so if you could design the system so there was no stagnant water, then it wouldn't grow again, you know. So all of these aspects play into this.
Another factor, Alan, is the water velocity.
Right.
And I think that people who have been doing the micro channel cooling with a cold plate,
Yeah.
they have just very a small water velocity. But when my case, where I'm just flushing water between boards, I think the velocity can be quite high, like maybe
So,
two,
how fast?
maybe 2 meters per second.
2 meter. What's that in liters per minute?
Oh, so it's the server is 200 gallons per minute.
200 gallons per minute. But that's the entire.
That's a server. So that's an 18-inch wide machine, 5 inches tall.
Yeah, and obviously the flow is a function of how much fluid you've got flowing overall, right? So we've got a very small area. So in terms of gallons per minute over one module, you can have a high flow rate, but relatively little fluid, I guess.
Yes. Yes.
So that was that. So the growth is a key aspect, and I think, and then, by the way, I think this is where Europe. I'm presenting at Europe, and I am presenting. I'm giving people an update on what we're up to, but I was going to do a little. I've only got 15 minutes, or even after the handover period, I've got like 10, 12 minutes. But I was going to do a piece on the thermal and a piece on the interconnect in the presentation. But I just think Europe is much more sustainable, aware, and focused.
Yes. Yes.
And
Environmentally. Yes.
environmentally focused. And
yes.
I think that if they understand the challenges of water, and they still don't like all of these extra fluids, then
chemicals. Yeah.
Chemicals. Sorry. Then research into how do we use the pure water. Is there a way where you can design a system where you have a good implementation, but you don't have the issues, and you don't need the chemicals? Then that would be something they would fund.
Yes.
I mean, yeah, I mean, in terms of us getting this funding, I guess it's they're all geared up for like cyber type stuff, you know, where you can get money. But this OCP trying to do it as an open community, there just doesn't seem to be a business model that allows a group of companies to try and crack this in the open for the greater good, rather than just a company. I mean, my biggest concern is if we don't do all of this holistically, the power, the thermal, the interconnect, all of these aspects of computing, if we don't do them together, if we all go away in our silos, you'll have little companies that might have a fantastic solution, but just can't get anybody's attention or can't get money because it's too big of change. Maybe they'll get bought by NVIDIA, so great for them, but great for great for the proprietary NVIDIA solution or whatever. But we don't get the. I'm after the greater good. I mean, that's me. It's not about money for me. It's about democratizing our industry a bit. Oh, I've lost you. Hello. No, I lost you there.
Yeah. So I just wanted to say that I'm also connected to a group that's managed by SRC, that's Semiconductor Research Corp.
Oh yeah.
And their program is called MMI. Something
I met those guys. I met the CEO. I went over to see them actually. I went to their offices in North Carolina.
Todd somebody. Todd.
Oh, that's it. That's it, Todd. Yeah.
Yeah. Now, I'm a little nervous because there was a lady from the government yesterday, a very impressive lady from the Commerce Department, and she was listing off all of these CHIPS Act programs, and she didn't mention that one.
All right.
And that's a big oops, you know. I'm going to be attending the next meeting of those guys, and I hope they talk about that.
Right.
But here's another thing: when they believe that the ground rules are that the government requires, I forget what they call it, but they only provide a percentage of the money.
Right.
And it may be less than 50%.
Yeah.
Okay. It's
Yeah.
still valuable, but it's, you know.
Well, it means you've got to find the other 50%, right?
That's right. Yeah. And what they're saying is that some of the big companies should step up and help fund the 50%.
Well, that's the other thing we've got, right? I mean, the big companies have got their gravy trains, and
yeah,
what we're doing,
yeah,
they're happy doing everything in their own little silo, especially NVIDIA, obviously. I mean,
yeah, right.
They're leading the charge, so
They went up $60 yesterday, $60 a share.
that's yesterday.
Yeah,
Oh my God.
yeah. But anyway, so I don't know, NAPMP, that question was asked, you know, do we have to have to have matching funds? And the answer was no.
Oh, right.
It was, it's encouraged, but not necessary.
Okay. Okay. I don't know how to go about it. I mean, we need some champions that like what we're doing, that know how the government runs, and would help us drive this. I mean, that's
Well, I think maybe you're doing something that's smart, and that is, it looks to me like everybody else is scrambling to get a piece of the CHIPS Act funding, and you're going a slightly different path where you're going for DOE funding, and that's
well.
I think it's separate from CHIPS Act, isn't it?
I got the impression it was, well, the money for this New Frontiers is from CHIPS Act. I did hear that.
Okay.
I wouldn't like to swear by it, but I certainly heard it. Whether I heard it third hand or I heard it straight from the horse's mouth, I can't remember.
Or even if it's from the same fund, it's $11 billion. It's a very big amount of money. And
the CHIPS Act money, right?
That is, yeah. Of course, most of that's going to wafer fabs, but
Intel.
Yeah. Well, just in this morning's paper, they canceled 2.5 billion going to Intel.
Oh, did they really?
Yeah.
Okay.
They said I didn't read it all carefully, but they said we want this money to come from CHIPS Act rather than from, I think it was rather than from DOE. But okay, so there's a lot of maneuvering about all this. But I think that if you're focused on the defense support, it might be in your favor because there's so many people trying to feed at the other trough.
Yeah, right. Yeah.
And the defense people could have, well, I could have a longer term view. Okay. One of the things that came out with this NAPMP yesterday is that they're pushing very, very hard to get to commercial product within 5 years
Right.
that's built in the US and sold internationally. Okay. Now 5 years is a pretty short time for some of the things that we want to do.
So when you say that, if they're looking at product, if they're only looking at chips in a package, you haven't got a product. They got to be thinking about the complete system, haven't they?
They are.
So why you said at the beginning that you didn't think that we fitted under their umbrella of activities?
Well, so there's multiple phases, and they've only so far introduced the first phase. And the first phase is substrates and materials. Okay. And this, I think, is very closely connected with hermetic coatings, which is what I'm doing, right? But yours is going to be more, I think, better aligned with a system design for manufacturability and energy efficiency, maybe.
Right.
So
Okay.
I don't want to tell you not to do it. That's the last thing I want to do. I just got the impression that this first one is very much related to the substrates.
Right. Well, that was
So
one of the areas I was talking to Subu about because he is a substrate specialist, and that was where get rid of the package and make the entire module the substrate is one of the things that I've been touting as well. I mean, again, there's so many facets to what we're doing.
That's right.
Okay. Well, just maybe switching gears back to the technical side. So the other thing I did is I started looking up vacuum pumps. And it turns out that pulling 0.2 bar is pretty damned easy. There's a ton of different types of vacuum pumps out there. And I got, again, I was using ChatGPT to do this, so it was really pretty good, to be honest. There it is. Liquid cooling solutions, there we go. Specific pump selection. So this liquid ring vacuum pump is, but the trouble is they're actually pretty big pumps. They can pump quite a lot of. So there you go. So there's a 30 cubic feet per minute is equivalent to 850 liters a minute vacuum pump. Now, I worked out that we needed about, in an eight module column, we would probably need no more than 50 liters per minute.
Uh-huh.
And the pumps that you buy, the smallest pump, there was a company that does this particular liquid ring vacuum pump, and their smallest pump did 850 liters per minute.
Okay.
So I was thinking, well, does anybody make such a small pump that does 50?
Right.
So that if you could put a small pump on each of our vertical loops, that would be pretty good. And I guess if you did get an issue, you just lose 8 modules, right?
Yes. Yes.
And I think from a serviceability or a downtime situation, that would be, losing one column of 8 modules may not be an issue.
Another thing you could do is have a manifold and then have a big pump that serves multiple columns.
Yeah, you said that, but I'm not sure how that would work with a liquid ring vacuum pump. They'd have to all be on the same, and unless you had one pump and you had like 3 of these compression wheel, or 10 of them with 10 different loops that they're all driving. So one motor drives all the, but then that wouldn't make sense either, because you might have different vacuums.
No, but let's say all of these channels are merged into a single wide channel, and
right.
in that wide channel you have your special liquid ring vacuum pump. Okay, it creates a vacuum. Well, that vacuum is going to be transmitted through the water and through the manifold to all of the channels.
Yeah, so I think that would be a different type of vacuum pump.
Oh,
There was about 4 or 5 different types that I identified, and
okay.
some of them can pull tremendous vacuums, look like a literally take all of the 100% vacuum or whatever you call it,
Yeah.
virtually. But when I asked the question about 0.2 bar, it came back of, oh, that's pretty trivial, and so it recommended that these liquid ring vacuum pumps would probably be the best.
Okay.
Now, the only other thing on this as well is these pumps are pretty power hungry.
Yeah.
So, these pumps are like 0.5 kilowatt to 3 or 4 kilowatts, depending on the load, I guess.
Yeah.
The smallest pump. And so that's a pretty substantial chunk of our 8 modules in a column at 2 kilowatts each. It is 16 kilowatts.
Yeah.
So the pump itself could be a freaking problem. So power energy wise.
Yeah. But you have to break eggs to make an omelet, right?
Right. Well, yeah, it's what is the win for the what is the bang for the buck, I guess is the question, right? Exactly.
Yeah.
I mean, obviously, well, they've got PUEs. I mean, that this is where they got these PUE ratios down to like 0.03 or whatever, right? So the power to run the air conditioning in a room is only 3% of the energy to run the compute. So I mean, our PUE would be horrible with this pump.
Yeah.
But there was an argument from Europe where they were doing heat pumps, so that added to their PUE. So their PUE was up to like 1.3 or something. But their energy reuse effectiveness, their ERE, which is a new measure of how much energy can you recover for other purposes, for using for other purposes, and that their ERE was through the roof. So they were overall a better solution than the energy labs here.
Yeah.
Where they didn't do any heat pump and they just recovered what they could. So they had a great PUE, but their ERE was terrible in comparison.
Yeah.
So it depends on what you're measuring, right? So, but anyway, so as you dig in, you do realize. So what I was going to try and do on the presentation is like literally I'm going to have like 3 or 4 minutes on the thermal piece. I was just going to try and show the loop. I was going to show a picture of the pumps, the vacuum pumps. I was going to say, in theory, you can pull this vacuum. I was going to give a high-level overview of what it is we are trying to do, and I was going to give a call for any European interest or experts to say, look, we want this to work for water, 100% water. This is sustainable in energy. This is the ideal solution, but everyone's moving away from it because of these problems. So we need to solve these problems in a brand new design, and we've got an opportunity with what we're doing to maybe design the things so that we eliminate these bacterial and material buildup issues.
Yeah, I think that's a cool idea.
Right. Thanks.
I mean, the idea of presenting it in Europe and perhaps engaging someone with an environmental motivation.
Yeah, that's the idea.
Yeah.
So yeah. So I mean, to be honest, it's been quite good. The conversations we've had. Last week's conversation, was it Mike Felton was in? And with Trent. This is the nice thing about discussing these things in the open community, is you get intelligence that you just would never even think of by trying to do it by yourself.
Right.
And
that's right.
And I think at least that's the beauty of trying something that's brand new. You get plenty of people that tell you you're full of shit and it can't be done.
Right.
So you find all the problems before you actually encounter them yourself.
Yes.
Because people are delighted to tell you that won't work because.
Right. Right.
And it's like, okay, all right, thanks for that little bit of intelligence. Now, okay, give me another way it won't work. You bring all the way it won't work.
Right.
And then you make it work.
That's right. Yeah.
So I don't mind the people telling you it don't work. I learn every time somebody tells me it won't work.
That's right.
That's the beauty of being the naive one in the room. So I mean, from your perspective, your little experiments, have your little load things come in yet? Have you managed to start your?
No. So I'm still probably 5 weeks away from the fabrication being completed.
Okay.
So then I go into the testing mode.
So you're doing little tiny load cells. You're doing very small experiments of this.
The size, each one is the size of a microscope slide.
Right.
2.5 inches by 1 inch.
So you're building a little water chamber around that, are you?
I just have a beaker of water.
Okay.
Yep.
And then you're boiling it, or are you pulling the vacuum in the beaker, or?
No, I'm not pulling a vacuum. So I'm back to not using a vacuum.
Oh, right. Okay.
Yeah. But yeah, I think I can get to a very useful point where I can say, in the study of hermetic coatings, all of these different things have been proposed, but my test data shows that this one is the best.
So this is along the same lines as what Ninad has already been doing, right?
That's true, it is, yes. But I'm doing things a little differently. So, for example, I drive each part until it dies.
Okay.
And that's a very useful data point.
Yeah, you see what the failure point is, I guess.
Yeah. And anyway, I'm kind of comfortable with where I am. There's still some risk in the processing, and I'm holding my breath, but this is the way it goes.
Right. And so your view is the same as NAND. The efficiency of having a hermetically sealed, then a layer of copper is so much more efficient, lower resistance, thermal resistance in a traditional thermal grease in copper slug.
At a high level, that's true, but he's taking heat out the bottom of the chip, and I'm taking heat out. Excuse me. Yeah. His heat goes. His copper envelops the chip on all sides.
Right.
And he's relying on heat spreading. Okay.
Out.
Yes.
In a planar sense.
Yes. And I don't want to rely on heat spreading. I call it orthogonal cooling, where the heat comes out the back of the chip and I ignore any heat that goes to the substrate.
So you're saying is the flip chip package. So this is a silicon. This is a substrate with a flip chip bonding, and you're coming off the top.
That's right. Orthogonally, the heat's going straight up.
Right. So I mean, essentially, he's got the same, but like you say, I didn't realize he went underneath as well.
Yeah, and
is he going underneath as well? Is he? Wow.
He has, and
wow. I thought you would have some underfill stopping it from having to go under. So he's actually making the underfill these little copper channels.
Yeah, now it may work because if the chiplets are small, you don't need the underfill.
Yeah, but the only thing is what will that do with the dielectric, the impedances of some of these high-speed signals coming from the?
Yeah, that's a good question. Yeah, but he's, yeah. So I think there are some big differences between his model and my model. And this is kind of good because we can compare, which one works better.
Yeah.
Yeah.
Well, yeah. So once you've got a sort of a top level principle of how to do something, then there are the subtly different ways is where people can bring their own IP to the game, right?
Yeah.
The way is more efficient than your way.
Yeah. Right.
I mean, so by the way, just on that note, this FPGA emulation is where the first use case that I'm beginning to get more and more committed to. And the nice thing about the FPGAs is they're actually not that hot running. That like they're well under 500 watts, probably in the 200 to 300 watt operating region. And so we could cool this quite effectively just with a copper slug with the water flowing through the copper with a thermal grease, right? So, but the design of the HPCM module allows us to do the immersion chamber with the likes of yours and Nanad's conformal coating approach, as well as redesign the lid with the same water connections, but just have the water flowing through the copper of the lid, and it all be sealed in the lid, right? So, therefore, I'm thinking that maybe this conformal coating is a little bit too researchy for us to get a product, a proof of concept out, but we've got the fundamentals. If we can build this product and we can cool the sub 500 watt chips effectively with more traditional copper water chambers.
Yeah.
And then we can quickly flip over the lid to a mini immersion chamber for your conformal coating or Nanad's or a mixture of both or whatever. Then we could do that.
How big are these FPGAs?
Oh, it's a big one. 78 by 78 is the size of the package.
And that package is dissipating up to 500 watts?
Yes.
Okay, so it's true. That's an easy cooling situation.
Right.
Yeah.
Right.
So, Alan, I'm going to skip out a little bit early today.
Yeah.
My wife and I walk that dog every morning, and I've been neglecting my duties.
All right. All right. No, well, good discussion. Yeah, we'll plod along. So thank you very much.
Right.
your help.
Thank you.
Take
Bye.
care.